You ever stop and think about the technology we use every day? Some of it seems, well, almost impossible. Today, we're going to pull back the curtain on an invisible force that makes it all work by tackling a few puzzles that seem to completely break the laws of physics.
Okay, let's start with something wild. Picture the inside of a jet engine. You've got these turbine blades spinning like crazy, and the gases blasting past them are hotter than the melting point of the metal itself. I mean, literally hot enough to turn the blades into liquid. So, how in the world do they not just, vaporize in midair? All right, now let's switch gears to manufacturing solar panels. To make one, you have to pull this perfectly thin, solid sheet of silicone right out of a pool of molten, glowing silicone. I mean, think about that temperature shock. It feels like it should just shatter into a million pieces, right? But it doesn't. How do they do that?
And now, let's bring this right into your hands. The device you're probably watching this on, your phone, your laptop, has a processor inside that's just cranking. Billions of calculations every single second. That generates a ton of heat in a super tiny space. So what's stopping that little chip from just melting itself into a puddle of goo? So we have a jet engine, a solar panel factory, and your computer. Three totally different worlds, right? Aerospace, manufacturing, electronics. But the answer to how all three of them work is the exact same thing. It all comes down to mastering one single fundamental idea.
And that idea is heat transfer. Simple, right? But it's not just about things getting hot or cold. It's about the control of that heat. Being able to move thermal energy exactly where you want it, when you want it. That control, that's the secret sauce behind, well, pretty much all of modern technology.
So what is it really? At its heart, heat transfer is just energy on the move because of a temperature difference. That's it. Heat always, always flows from a hot place to a cold place. It's not magic, it's just physics, specifically the first law of thermodynamics. You can't make energy disappear, you can't create it out of thin air, you can only move it around.
Okay, so if energy is on the move, how does it travel? Well, it turns out there are three main ways. Let's start with the one you're probably most familiar with, conduction.
Conduction is basically heat transfer by touch. Think of all the molecules in an object as a huge crowd of people standing shoulder to shoulder. If you push someone at one end, the ripple goes all the way through. It's the same with heat. When one end gets hot, its molecules start vibrating like crazy, and they bump into their neighbors who bump into their neighbors, and that energy gets passed down the line. That's exactly why a metal spoon in a cup of hot coffee gets hot all the way up the handle. But not all materials do this well. Just look at this chart. The difference is massive. Over on the left, you have metals. They are fantastic conductors. Why? Because they have all these free-floating electrons that can zip around and carry heat energy super fast. It's like a highway for heat. But then way over on the right, you have things like gases or insulation. Their molecules are way farther apart or locked in place. Passing energy from one to the other is really, really hard. And that, in a nutshell, is how insulation works. It's just a material that's terrible at conducting heat. Okay, so conduction is when heat moves through a substance. But what if the substance itself can move? What if the hot molecules can just pack up and leave? Well, that brings us to mode number 2, convection. Convection is all about heat transfer in fluids, so think liquids or gases. Imagine a pot of water on a stove. The water at the bottom gets hot by touching the hot metal. That's conduction. But then that hot water actually moves up to the top, carrying its heat with it. It's like a delivery service for thermal energy, so it's conduction plus actual movement. And convection comes in two main flavors. You've got forced convection. That's when we force it to happen, using something like a fan or a pump. The fan in your computer is a perfect example. It's blowing air to carry heat away. Then there's natural convection. This happens all by itself. Think of a radiator in a cold room. The air around it gets warm, becomes less dense, and just naturally rises. That creates a current that circulates heat around the room. No fan needed. Now here's where it gets really cool. The secret to making convection work well is understanding this tiny, invisible thing called the thermal boundary layer. It sounds complicated, but think about this. If you look at a fan blade that's been spinning for a while, there's always a thin layer of dust right on the blade that just won't come off, right? That's because right next to any surface, there's a super thin layer of fluid, air in this case, that's barely moving because of friction. It's stuck. So for heat to get away from the surface, it first has to conduct slowly across that stagnant layer. The rest of the fluid can then whisk it away. So the whole game in engineering is to make that sticky layer as thin as humanly possible. The thinner the layer, the faster you can get rid of heat.
All right, that brings us to our third and final mode, and this one is different. It's a real game changer. Unlike conduction and convection, which need stuff to travel through, this one doesn't need anything at all. We're talking about radiation.
Thermal radiation is just pure energy, shooting through space as electromagnetic waves, kind of like radio waves or even visible light. The wild part is that it can travel through a total vacuum. And here's the kicker. Everything, and I mean everything, that has a temperature above absolute zero is constantly shooting out this radiation. You are, I am, this desk is, everything. And if you need proof of how powerful this is, just look up. The sun. All of its warmth, all the energy that powers our entire planet, has to travel 93 million miles across the empty vacuum of space to get here. That whole journey? That's 100% thermal radiation. It's incredible. So there you have it, the big three: conduction, convection, and radiation. But here's the thing. In the real world, these three are rarely working alone. They're a team. And to solve those really tough engineering puzzles we started with, you have to understand how they all play together. Let's go back to that impossible jet engine blade. How does it survive? Well, it's an absolute masterclass in using all three modes at once. First, engineers use forced convection. They pump cooler air through a maze of tiny channels inside the blade. Then, that air shoots out of microscopic holes on the surface, creating a thin, protective film of cool air. Remember that boundary layer? They're basically engineering a custom insulating one. And on top of that, the blades are coated with special ceramics that are terrible at absorbing heat from radiation. It's this beautiful, complex dance between all three that lets a piece of metal survive in a place it should have melted. And you see this same kind of thinking in something you might have in your own house: high-performance insulation. It looks simple, but it's fighting heat on all three fronts. The solid plastic material is designed to be bad at conduction. The tiny honeycomb cells trap air so it can't move around, which shuts down convection. But even then, the inner walls of those little cells are still radiating heat at each other. So engineers have to account for radiation too. It's a total system. And look, getting this stuff right really, really matters. Take our computers. Just to make the aluminum heat sinks and power the little fans inside all the world's PCs, we burn through over 1 billion kilowatt hours of energy every year. Think about that. That's a staggering amount of power used for one single purpose: just moving heat around. So now I'm going to throw the challenge back to you. You've got the toolkit now: conduction, convection, radiation. The next time you hear your computer fan spin up, think about it. How could you use these principles to design a better solution, one that's silent, more efficient? Because whether we're talking about building a silent computer or designing materials that can survive inside a fusion reactor, the answers are all hiding in the invisible flow of heat. The next big breakthrough is out there, just waiting for someone to put these pieces together in a new way.